Hello, my name is Kevin Chen, and this is Lab 5, Magnetic Braking with Faraday for Physics 2212 at Georgia Tech. In this lab report, we're going to first introduce the purpose and results. We are then going to move on to some key physics principles, and then to the experimental procedure and experimental results. And then after that, we're going to move on to the computational model, and then the assumption and experimental errors. And then we are going to answer some discussion questions and move on to the conclusion. The purpose of this lab was to model and observe Faraday's law to explain how an EMF in a conductor is induced through a changing magnetic field when a magnet falls through a copper tube. And we created a computational model to compare with the experimental results. And moving to the results, we found that the experimental time was 12.95 seconds, and with a magnetic dipole moment of 1.91 amp meter squared, which was the magnetic dipole moment calculated from the previous lab, it took 37.61 seconds to exit the tube. And since the time was so off from the experimental data, I manipulated the magnetic dipole moment to obtain a time of 12.91 seconds, which was closer to the experimental time of 12.95 seconds. And the magnetic dipole moment from the previous lab did not accurately represent the effective dipole moment for the interaction between the magnet and the copper tube, which is the reason why I've manipulated the magnetic dipole moment value. Going into the key physics principles, we have Newton's second law, where the change in momentum is proportional to the net force. We have Newton's third law, where for each force there's a force that is equal in magnitude and opposite in direction. The Biot-Savart law describes how a generated magnetic field is related to the magnitude, direction, length, and distance of an electric current, and is used to calculate the magnetic field exerted by a magnetic dipole moment. Faraday's law relates EMF to change in flux. Lenz's law states that the direction of an induced electric current produces a magnetic field that opposes changes in the initial magnetic field. Finally, we have Ohm's law, which states that the current through a conductor between 2 points is proportional to the potential difference, and the equation is V equals IR. So for the experimental procedure, a magnet was dropped down a copper tube, and we started a timer once the magnet was dropped, and we stopped it when the magnet fell out of the other end. And for the initial conditions, the length of the tube was 1.05 meters, the width of the tube was 0.001 meters, the inner radius of the tube was 0.0065 meters. The mass of the magnet was 0.023 kilograms, and the magnetic dipole moment, mu, which was calculated in the previous lab, was found to be 1.9 amp meters squared. So for the experimental results, we had 3 separate trials for dropping the magnet and timing how long it took to travel down the copper tube. And so the average time that we found was 12.95 seconds. Moving on to answer a few checkpoint questions. Why can't we use a ferrous tube, like for example a steel pipe? So ferrous metals contain iron, so the magnet would feel an attractive force to the tube, and it would cause the metal to stick to the tube or produce inaccurate results. And next, what happens to the magnet, and how does this compare to a magnet falling in free space without a tube? So as the magnet falls through the copper tube, the change in magnetic flux induces currents, which creates a magnetic field that opposes the magnet's motion, and this leads to a magnetic force that points upwards against the force of the gravity, bringing the magnet down. And this reduces the acceleration of the magnet and can lead to lower terminal speed. And so the magnet would take longer to fall than it would in free space without a tube. So moving on to the computational model, we have the physical constants, which is Km, resistivity, which was for copper, and we have G for gravity. We have the length of the tube divided by 10, so that the computational model would be able to simulate the magnet falling properly. And we have the width and the inner radius. Next, we establish a function that calculates the magnetic field exerted from the magnet using the Biot-Savart law. And we also establish the function for calculating the rate of change for magnetic flux going through each ring caused by the falling magnet. So in step 4, we calculate the current induced by each ring from the falling magnet, and then for steps 5 and 6, we calculate the force exerted on each ring that carries a current, and then Newton's third is applied to calculate the force exerted on the falling magnet by the tube. And then for step 7, it establishes an expression for the net force, so it's just the magnetic force plus the force of gravity. In step 8, we use Newton's second law to update position and velocity in the code to produce a graph. So these were the computational models from the 2 magnetic dipole moments. So as you can see from a dipole moment of 1.115 amp meters squared, the time was 12.91 seconds, which was close to the experimental data of 12.95 seconds, and the magnetic dipole moment of 1.9 amp meters squared, which was calculated from the previous lab. The total time to exit the tube was 37.61 seconds, which was very far off from the experimental data that we collected. And a reason for this was that the mu mag from the previous lab was not aligned with the magnitude of the magnetic dipole moment needed for this lab, because it's a different scenario since the magnet is falling down a copper tube, and so the approximations would be different. And so we had to adjust the magnitude of the magnetic dipole moment so that it would be closer to the experimental data. Going to the assumptions and experimental errors, we're assuming that the only forces are from the magnetic field and gravity, and we're also assuming that the dipole moment is aligned with the axis of the tube at all times, so it isn't hitting the sides of the tube. And the experimental errors is that we're not factoring in external forces such as air resistance and friction when the magnet hits the side of the tube, as well as human error when timing. So what happens to the dynamics of the system when you flip the magnet around? So the magnet will still fall, so its motion will not change, but the induced currents would be flipped since the magnetic fields would be traveling in opposite directions. So how does the total time in the tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? So with my original magnetic dipole moment of 1.91 amp meters squared, I had a time of 37.61 seconds, which is much greater than the experimental time. And then when I manipulated the magnetic dipole moment to be 1.115 amp meters squared, I had a time of 12.91 seconds, which is slightly faster than the experimental time. So in theory, the computational model should be faster since it did not account for friction and air resistance. And the computational model could be made more accurate by factoring in forces like friction and air resistance. And the accuracy of the experimental time can be improved by improving the data collection methods or increasing the number of trials. So what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So the slope is larger at the beginning and end of the velocity versus time graph, since gravity is larger than the force of the magnetic field, and the forces are equal inside of the tube as the magnet is traveling down, which causes the magnet to have a constant velocity and produce a flat area on the graph. So moving into some discussion questions, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So the magnet would fall slower since there's a stronger induced current and more intense magnetic field. By Ohm's law, decreasing the resistivity decreases the resistance, which would increase the current flowing through the tube. And by Lenz's law, increasing the current would increase the force exerted on the magnet, which would cause it to fall slower. And the next, what if the holes or slots were cut into the tube? How would this affect the ring currents in your model? So the magnet would fall faster since there's a weaker magnetic field. The holes would disrupt the induced current loops, and the force on the magnet would decrease and the magnet would fall faster. This brings us to the end of Lab Report 5. Thank you for watching.